Hi everyone, good evening to all. Today we're going to discuss about the construction of velocity triangle of centrifugal pump. I'm hopeful that this video is going to be very interesting. So please do keep watching until the end. Subscribe my channel. Thank you. So let's begin the discussion. So this is the inlet velocity term that is for construction for velocity triangle, and this is outlet velocity triangle. One for dash is shown for the ideal case, and another is without dash is considered for the actual case of outlet velocity triangle. Velocities are measured in meter per second, and for the blade angle it is in degree. So these are the dimension for D1H, impeller hub diameter, root diameter D1M, impeller inlet mean diameter, D1 diameter impeller inlet tip diameter, D2 impeller outlet tip diameter, and N is RPM. So inlet velocity triangle, so inlet mean absolute velocity C1 is drawn in axial direction, which is shown as this is C1. Then inlet mean impeller tip velocity, that is V1. V1 is a pi d1m into n upon 6 into 1000, and which is drawn in the direction of rotation, that is u1, which is shown here. Then inlet mean relative velocity v1, join the endpoint of u1 and endpoint of c1. This will give the v1, that is inlet mean relative velocity, and beta 1 is the blade angle, which is measured from the axial, which is a mean position. So inlet velocity triangle is drawn at the mean blade height. And inlet mean axial velocity CA1, which is axial component of C1, which is same as C1, and inlet mean whirl velocity CW1, since there is no component for tangential side of C1 because C1 is in axial. So CW1 is 0. Now ideal outlet velocity triangle, so it is shown as a dotted. So ideal outlet relative velocity V2 dash is drawn considering the outlet blade angle, that is beta 2, from the radial direction. Then outlet impeller tip velocity U2, which is pi d2 n upon 60 into 1000, and draw in the direction of rotation, which is U2. Then ideal outlet absolute velocity is C2 dash. We just join the starting point of V2 dash and end point of U2. This will give the value of ideal outlet absolute velocity, that is C2 dash. Now it has two components. One is ideal outlet axial velocity, that is CA2, axial component of C2 dash. Similarly, the ideal outlet whirl velocity CW2 dash, which is the tangential component of C2 dash, which is shown here. Then outlet, we have to now draw the outlet velocity, that is actual outlet velocity triangle. So outlet impeller tip velocity, you have to draw the tip velocity considering the slip factor, and slip factor is defined as the ratio of ideal and actual outlet whirl velocity. That is a this. So we have to considering, so draw the u2 considering the slip velocity, that this we have to give how much this is slip. Then outlet relative velocity is v2, we have the starting point of v2 dash to the starting point of u2. This will give the value of v2. Then outlet absolute velocity c2, join the line the starting point of outlet relative velocity, this is a starting point, and end point of u2 considering the slip factor. So this will give the value of c2. And blade angle outlet velocity angle, that is theta 2, is measured from the radial direction, which is shown as theta 2. Then outlet axial velocity, axial component of outlet velocity is called outlet axial velocity, and here actual axial velocity for the ideal and actual both are same. And the tangential component of outlet velocity absolute velocity give the outlet whirl velocity. So this is whirl velocity CW2, and this is ideal CW2 dash. Information about inlet velocity triangle. So both the inlet velocity triangle are same. This can be drawn like this or this. So thank you for watching.